This is the bumper box of goodies that goes by the snappy title of Multitex Multi-Connect Conduit IoT Starter Kit for LoRa technology. As the cover suggests, it can quick start your Internet of Things idea with business insight, analytics and visualization in minutes. We will not start a stopwatch to test this claim, but in this series of videos we will examine the complete process of establishing a full IoT connection that this kit facilitates, and in the process explain how we can experience firsthand the fundamentals of the underlying LoRaWAN technology. Unpacking the contents reveals a confusing array of the central unit, the conduit, a pair of M.dot boards, an M.dot Universal Development Kit, an M.dot Micro Development Kit, an M.dot box, a GPS module, several small antennae, mains power supply, a range of interconnecting cables, and copious paperwork. At the centre of the system is the conduit. I'd like to call it the conduit box, as it's obviously a box, but Multitech insist on calling this handheld testing unit the box, so we must refer to this as the conduit. The conduit is a flexible and compact unit with a string of indicators and a reset button on the front, and a whole array of connectors on the rear. Working from left to right, these are for cellular connection, Wi-Fi, micro USB, power supply, Ethernet, full-size USB, GPS, RF, and ancillary. Most of these connectors are mounted directly onto the chassis, but the hardware flexibility of the conduit is also based upon these two slots that allow optional additional cards to be inserted depending upon your connection requirements. The starter kit comes with a LoRa accessory M card already inserted into the right-hand slot, although it does not matter which slot is used as they are identical. The LoRa radio port is the one simply labelled RF. An improvement will be to more clearly label this LoRa. Together, these all form a well-designed and very well-constructed base. But it's not a box, it's a conduit containing an M card. This is the box. We will become familiar with the strangely convoluted naming scheme and Multitech's little quirks as we proceed. The world is already full of things, but the Internet of Things is where things are basically any normal thing but has a sensor or actuator, a certain amount of intelligence, and the ability to communicate on the Internet. We could use the familiar smoke alarm as a starting point for the definition of a normal familiar thing. It has a sensor, the smoke sensor, and the intelligence to understand when a dangerous amount of smoke has been detected. It can communicate with a shrill audible alarm or even quietly pip intermittently, warning that its battery is failing. Although functionally this smoke alarm has all the elements of a thing, it does not really fulfill the criteria of a fully qualified thing. To fully participate in IoT, this smoke alarm needs to be able to communicate with the Internet and be supported by services or applications that combine to enhance its performance. This may be to summon help from a local fire brigade, activate sprinklers, or just say, message your mobile phone. 4 qualities that make this a fine example of promotion from an ordinary thing to an IoT device is the need for a long battery life, shared connection over a wide area, low cost, and it only needs to send a limited, if important, amount of data. It's convenient if this battery-powered unit communicates using radio, and here there are a number of options that may be employed. Bluetooth, Wi-Fi, LoRa and cellular are 4 alternatives. Whatever the choice, the signal has to be received and then passed on to the Internet. These very small messages are often referred to as packets. These packets are transmitted onto the Internet and need to be processed and forwarded. Bluetooth beacons and Wi-Fi access points are all familiar inside the home, whilst mobile cellular is everywhere. But here we will just consider the LoRa option. LoRa is the low-power radio signal that can communicate over distances up to 15 kilometers. Unlike Bluetooth, that is very short range, or Wi-Fi, where the number of devices in any area is limited, a single LoRa access point, known as a gateway, can handle tens of thousands of devices, or N devices. The elements of the starter kit should now start to fall into place. The M dots are the small radio devices used in the thing to form an N device, and the conduit is the gateway that receives the signal and passes it on to the Internet. That array of connections on the back can now be understood. The conduit can talk to Bluetooth things, to Wi-Fi LAN things, and LoRa things. These could be called the front-end connections. On the other side, the back-end. The conduit may forward packets onto the Internet using several options. It can use another Wi-Fi connection, its hardwired Ethernet port, or the mobile phone network. It is a very well designed, comprehensive and flexible unit. Once on the internet, any packet can be sent to another device or onto the cloud for storage or more processing. It can also be sent, say, to an app on a mobile phone. Packet forwarding through any of these routes is a lot of functionality, but the conduit has even more capability. Rather than forward packets onto the internet, the conduit has what is known as a server mode. The server mode does away with the need for the internet and can simulate the cloud-based system to act as a standalone system. This means that the conduit takes on a great deal of work of the network and application servers, but allows it to be used for testing or easily used independently across a single local site without internet connection. Meanwhile, the box is a handheld unit that can be used to act as a fully functioning thing. It contains a radio and several internal sensors that can transmit atmospheric pressure, altitude, temperature, light level and accelerometer information. This is obviously essential if you're planning to deploy a low-power radio connection and is the subject of the rest of this video. The first step in preparing the startup kit is the configuration of the conduit. Fit the mains blades into the power supply module to suit your local supply. Selecting the correct antenna can be tricky as they all appear to be similar, but the kit contains a matching pair and these are the ones for LoRa operation. Fit one to the labelled RF on the plug-in card. The other can now be screwed onto the box for later use. Connect the power supply and power up. The conduit has a screw-threaded, secure power supply input jack, but does not have a power switch. It takes over a minute to load the operating system and applications, so be patient. Factory fresh, each conduit is pre-configured with a default static IP address of 192.168.2.1 with a web-based graphical user interface for setup, control and logging. Possibly the quickest method of accessing the graphical user interface is to directly connect a laptop to the Ethernet port with the standard straight-through patch lead, one supplied in the kit. Just interconnect the two devices directly. Both the yellow and green LEDs on the base of the RJ45 connector should light. The green LED proves the electrical connection, whilst the yellow LED flashes to show network activity. Unlike a typical domestic modem, the conduit is not set up in its default mode to issue IP addresses to attached devices, so a static device must be used to communicate with it initially. On a Windows machine, this typically means accessing the network settings and entering a static IP address and subnet mask here. 192.168.2.2 and 255.255.255.0 are acceptable options. Apply, save and start a browser pointing at http://192.168.2.1. At this point, you may be presented with a security warning. This is normal behaviour as the conduit will redirect your browser from the basic HTTP connection port 80 to the secure HTTPS port 443. Should the challenge appear, just select the Add Exceptions option or equivalent to avoid any further security challenges. A quick note. This behaviour is acceptable here, as this is a private development platform and we understand and can control the situation. It may not be wise to take such a cavalier attitude when working on the public internet. Once accepted, use username admin and password admin to enter the conduit. A fresh startup splash screen entitled First Time Setup Wizard appears to guide you through the initial setup configuration, requesting a new password and date and time values. The conduit has to be restarted once these are entered. Once rebooted, use the username admin and your new password to re-enter the conduit. Note that at this time of filming, we are using the Multitech Conduit Firmware version 1.4.3. This is important to note, as this video will make little sense if it's applied to earlier firmware versions and may not make any for versions yet to come, implying that this whole exercise could be futile. Anyway, the firmware has developed rapidly and for the better. Either way, the general principles explained here will remain broadly relevant. We will now take a brief tour of the menu before establishing the first link. This is the main home menu. At the top we see this is a Multitech Conduit Applications Execution Platform. This is an easy entry version of the conduit, and it's friendlier than the full fat alternative, the conduit called the M-Linux option. The exact model number is here, and the firmware level mentioned earlier is here. You can see that you're logged in as user admin here, above the logout link, and excellent search facility. By the way, the unit will automatically log you out following a period of inactivity as a security measure. We will complete a full tour of these menu options later. For the moment, we will concentrate on connecting a LoRaWAN device. Click on Setup, LoRa, to reveal the LoRa networking pane. You can explore the copious help pages that are available behind the context-sensitive question marks that appear all over this site. And later press the Reset to Default to remove changes you wish to remove and start afresh. Multitech have done a very good job of setting up every kit to work directly out of the box. Clicking on this pull-down mode reveals the option to switch between the two modes mentioned earlier, the network server and the packet forwarder, or the option of disconnecting entirely. The packet forwarder mode would be the usual method of running the conduit in a large network, and this is the mode where the radio signals received from the end nodes are assembled into packets and forwarded out to the WAN, the internet. Using the network server mode is where the conduit emulates the rest of the world by servicing the packets itself. This is what we will demonstrate here, so the default should remain left as network server. Scanning quickly over this section labelled LoRa Network Server Configuration, we see that the frequency band is set by default to 868. This is 868 MHz, the frequency used in the UK and Europe. Other frequencies are used around the world as shown, but here this unit has been pre-configured for our region. One of the reasons for making this video was to differentiate the UK and European settings from those more usually described for the North American situation. It perhaps should be repeated here. Multitech have done a good job personalising every kit in this version. Previously, the name and passphrase needed to be entered here, and then duplicated in the setup box for a connection to be made, but this is all now pre-configured in this kit. Nothing in this pane needs to be changed. Just scroll down to reveal this submit button that would be the normal way of recording any changes that had to be made. The LoRaWAN ability has been conveniently pre-configured. We now need to move on to confirm that the conduit is receiving and can process radio packets. For that, we need to turn to another graphical user interface that can be run at the same time as the control console on another web page generated by the conduit. It's called Node-RED, and if you've not seen this before and what it can achieve, you're in for a treat. Click on this Apps menu item to reveal this Manage App pane. Click the Enable tick box and then the blue button entitled Launch Node-RED. This status should change to running to confirm that Node-RED has been started. Again, this may take a few seconds to achieve. This should open a control screen on your access to the wonderful world of Node-RED. Our other videos on Node-RED go deeper into its operation and are given in the description below this video. For the moment, all we're going to do here is demonstrate how to get it working. At the initial security splash screen, enter the username admin and your password, as used on the main admin page, to reveal this screen. Node-RED has this palette of nodes on the left that can be dragged and dropped into this central design canvas. Click and drag this blue LoRa node and this green debug node onto the canvas. Click on the small grey output circle here and drag the elasticated orange wire onto the grey input circle of the debug node. We now need to make two small configuration changes to the nodes. Double click on the LoRa node and change the internal pull down to bytes and confirm by pressing OK. And then double click this debug node, select the complete message option to receive all of the message received, and again click OK to confirm. Finally, in the third column, select the debug tag to see all of the outputs from the debug node. This deploy button turns red when any node configuration has changed and needs to be recorded by the system before running. Start this updated configuration by clicking on this red deploy button. This green drop-down pane confirms deployment, and everything on the conduit has now been set up to receive and display any message detected. This green circle highlights the connected status. With everything now set up to receive, we can now try to transmit information from the box to the conduit so that it appears on this debug screen. It's now time to consider our thing, or in this case, our thing simulator, the box. Ensure the aerial is securely finger-type screwed into the connector, and as the kit is new, insert the 9V PP9 battery. Slide down the power switch on the left-hand side of the box. LED 1 should initially light green to confirm that the power is on, and then turn red to indicate that the box has yet to connect to a conduit. This blue LED 2 displays the status of the GPS system if one is detected in the box. It will flash until it acquires a lock with sufficient satellites. The GPS signals from the satellites are rarely strong enough to enter standard buildings, and certainly will not penetrate a screened studio like ours. It will therefore continue to flash and leave any data fields empty. The splash screen appears, followed shortly afterwards by this menu screen headed .box/EVB EU868. Select mode. The quirky numbering scheme means that the buttons at the base of the display appear to be reversed in order. Repeatedly pressing this one on the left-hand side, labelled SW2, scrolls continuously around the available menu options, which are currently Configuration, Survey Single, Survey Sweep, Survey GPS, View Data, and LoRa Demo. LoRa Demo is probably the quickest method of proving the link. Press SW2 to circulate through the menu options until LoRa Demo comes into line with the selection arrow. Select it by briefly pressing F1. The screen should briefly say Joining. The red-green LED flashes on the box as it attempts to connect to the conduit. It stays green once connected, and the join success appears briefly in the top line. Joining is a process that has to be completed before any other transactions are possible. It involves a number of interesting security processes that are covered more fully in a later video, where we go into an explanation of LoRa and LoRaWAN. If the join is successful, LED 1 stops flashing and turns solid green. The top line in the display changes to LoRa Demo and select TX method, where TX means transmit. The two options offered at the bottom of the display are interval and trigger. Interval causes the box to transmit periodically, but here we want to select trigger to set up a one-shot transmission each time SW1 is pressed. Initiate a transmission by briefly pressing SW1. The display now changes into a noisy mess, displaying two lines from the three-dimensional accelerometer and the pressure reading in kPa. On the next line is a fairly noisy altitude, here seen jumping over a range of a couple of metres, a slightly more stable temperature in degrees C, and finally another noisy light measurement in lux. Below this are the two options to move back through the menu or send data. So press SW1 briefly to send a data packet. LED 1 flashes red-green as the packet is resent, returning to green once completed. The process should only take a second or two before this appears in the debug screen. It's at this point we need to take a deep breath and dive into what all this gobbledygook means. The first thing is to relay out this text, as it will aid comprehension. This format is called JSON, JavaScript Object Notation. It's a format that's becoming increasingly popular, so time spent unravelling all of this punctuation is spent well. Encapsulated in these two curly braces and separated with commas, the list looks less intimidating. This list is a combination of timestamp, device and message identification, security, network and logging about the radio parameters used in the transmission of the packet. This element is the payload, and it contains the data that was the reason for sending the packet in the first place. All of these other items are called metadata, ancillary useful details about the transmission of the payload. The security, messaging and networking are all covered in a later video already mentioned. Here we will consider more closely the LoRaWAN operation. Here we will concentrate on just these radio-related details. The list is reduced to channel, data rate, frequency, signal-to-noise ratio, modulation and RSSI, receive signal strength indication. So let's recap to find out what all these mean. The world is full of things, and increasingly the world is filling with a new type of thing, and that's one that plays a part in IoT, the Internet of Things. A thing or things that are connected to the Internet. To be connected, they need to be able to communicate, and perhaps, unlike some of their human counterparts, need to have something to say, or at least listen. Examples include this sensor that measures river levels and forms part of a live river monitoring scheme. This air sensor that helps to produce maps of air quality, this personal health alarm, and this car sensor used to help drivers locate the only free parking space in the city. The list of applications is almost endless. The connection to the internet can take several forms, wired or wireless, and here from the wireless options we're going to have a look at one in particular, low power wireless area network. Bluetooth is too short a range for our application, as is Wi-Fi, that also consumes more power than we have available. Our aim is to power a thing that can operate from a single battery for almost a decade and still have the ability to communicate over a distance in excess of 10 kilometres. The mobile phone system offers this range, but at a price, both in battery charge and ongoing financial costs. Satellite communications has global reach, but is both power hungry and expensive. From the remainder, we want to test commercial offerings, late to market or failing technologies, and possibly the most important, any that don't operate with license-free radio. We discount closed proprietary technology and embrace those using international standards and collaborate as part of the open source community. No single choice fulfills all of these criteria, but the option that rises above all on the selection pile is LoRaWAN. LoRaWAN is an open networking standard constructed on top of a highly effective LoRa radio technology, and it is this that we will examine further here. In a perfect world, all communication links and equipment will be free, perfect, operate without power over infinite distances, providing unlimited bandwidth. In the real world, a more constrained but desirable list would be a large number of low-power devices working effectively, resilient to interference, that could simply associate with flexible localized access points, and, apart from the bandwidth requirements, this is what LoRaWAN sets out to achieve. LoRaWAN cannot stream video, but is very effective at sharing the small amount of available bandwidth amongst tens of thousands of users in a high-noise environment. It operates in a free and open manner, devoid of centralized control. We're already used to this type of regime with Wi-Fi. Wi-Fi has access points that can just be plonked anywhere into the network, with local users being able to switch to the strongest local signal. Hopefully, if an access point fails, an alternative source is automatically connected. Let's first refine some of the terminology used explicitly in LoRaWAN. Concentrators, base stations or access points are referred to as gateways. They perform the role similar to Wi-Fi access points, but have a range of about 2 kilometers in cities and 15 kilometers in rural areas. Note, though, that the current world distance record for standard LoRaWAN is over 200 kilometers. Every device sensor, thing, is called an endpoint. The radio link from the endpoint to the gateway is called the uplink, and in the reverse direction from the gateway is the downlink. The connection from the gateway to the internet is called the backhaul. All communications is carried out using very short messages called packets, with the packets passing through the backhaul to be directed by network servers that shunt them to the correct application server. Application servers do stuff. Stuff that's not a strictly technical term goes on now mainly in the cloud, where the results can form bigger data, be processed by applications, or be passed on to other end devices. Some apps may be seen using apps on mobile devices, whilst others may control other machines. This is known as machine-to-machine or M-to-M communication, and is included under another general term, IIoT, Industrial Internet of Things. If things use a LoRa signal, then where do we find it? Well, here in Europe, you can tune across the old AM radio dial, up through faithful FM, straight past digital and terrestrial television, to this region here, around 868 meg. So you can get your bearings. Here and here are the strong local mobile phone signals at 900 meg and 1800 meg. The height of the signals show how powerful they are, and all of this down here so low it's considered to be background noise, jiggling around randomly. It was only when I was preparing this video, finding examples of noise heard in tuning through radio dials or television sets, that I realised that these examples are from the past and have now all but disappeared due to push-button, remote-controlled digital and online access. We may not now experience analogue noise directly, but it's still there. Zooming in, we discover there's not a single channel allocated to IoT, but an array of 10 that may be used, all license-free, but they hide a further complexity. Conventionally, the powerful broadcasters are all tall, one station per channel. One station can be heard at a time as you tune across the dial. IoT radio uses a lower power signal, very, very low power, and then turns the signals on their side, separating them out across a broad range of channels. It's called spread spectrum radio and allows many stations to share all of the channels, again similar to Wi-Fi. This sharing comes with another ability. The more you spread the radio signal, the better the ability to ignore the random background noise. In fact, it gets to the point where the spread spectrum signal can still be recovered even when it falls below the background noise level. Impossible with conventional broadcasts. There are some other basic principles of radio that may be of use when we set up a LoRa radio link. The first is there are a whole range of radio signals. In fact, radio and television are both the same, and particular examples of what is known as an electromagnetic wave. These waves can be man-made or natural, and can be produced by just passing a current. Interference from thunderstorms, along with many other natural sources, can be heard coming from all around the world. In fact, part of this noise comes from the formation of the universe. But this is a huge but fascinating digression. We have already seen waves that can vary in height, strength or brightness, called amplitude, and in length. Some radios use very long waves, as sent out here from Droitwich for long-wave radio 4 on 1500 metres, that cross continents, or much shorter wavelengths, as here, on portable radios for more local communications. It can't be a surprise that the size of antenna is not just related to power, but frequency. As the wavelength of the signal decreases, the frequency increases. And here, on the full spectrum, we can see that we move seamlessly from old AM radio, FM radio, TV, mobile phones, satellite signals, higher still to a special electromagnetic wave humans are sensitive to, heat. Higher still to visible light, then the harmful ultraviolet causing suntan, thence to X-rays that pass through our bodies, and finally gamma rays that can destroy them.
Of course, we miss one, used in every kitchen, the microwave, that uses the same frequency as Wi-Fi. So, the basic principle here is that the antenna length is related to its operating wavelength or frequency. It's like an electronic gong, large and low, or small and high. There's nothing special about radio waves. They act like any other wave, just because we can't see them.
Let's take waves at sea and their effect on a series of boats. The large boat is not affected by the wave, it rides across the top. The shortest boat is more affected. But the worst experience is on the boat that is half a wavelength long. Its size produces the greatest rocking motion. This is exactly the reason why the TV aerial is the dimension it is. This distance is half a wavelength. There is another element. The radio signal was described as an electromagnetic wave, as it consists of two parts, an electric wave and a magnetic wave, that are coupled and travel together. To get the optimal performance, it's best if the size and orientation of the transmitting and receiving antenna are the same. Theoretically, as the receiving aerial is rotated, the incidence of the signal can reduce to zero as the size of the E-field diminishes. Consider a radio wave as it leaves a transmitter. It spreads out like a balloon, being stretched and becoming weaker as it expands. This loss is due just to distance. Walls, trees and the atmosphere itself can weaken the signal even further. We could see these obstacles producing radio shadows, and is one reason why placing an aerial high up is an advantage. We know that we can receive radio inside buildings and may have noticed how radios fade out as you drive into, say, a tunnel. Engineers refer to this reduction in signal as attenuation, and here is probably the first confusion for the uninitiated, and it's summed up in two letters, dB, the decibel. If we consider any transmitter connected by cable to an aerial and a receiving aerial connected by more cable to a receiver, it appears like this. The signal streams out, and let's add some obstacles, such as a brick wall and a tree, both of which cause loss in the signal, or attenuation. If we place a percentage figure on the loss of each stage, it could look like this. In order to sum the loss between the transmitter and receiver, or the total path loss as it would be referred to, then we would have to multiply all of the losses together. Not impossible, but potentially error-prone. Taking the logarithm of each loss and calculating the path loss reduces it to simple addition. It is possible to use decibels and impress people by referring to them without understanding or even having access to a calculator, and it works like this. Attenuation expressed in decibels is just a ratio. A loss of a half is expressed as minus 3 dB. Halve that again to a quarter and it's minus 6 dB. Halve that again and it's minus 9 dB. A gain of 2 is 3 dB. Double that gain to 4 is 6 dB. Double that again to 8 is 9 dB. See the pattern? A gain of 10 is 10 dB. And a gain of 100 is 20 dB. And a gain of 1,000 is 30 dB. Losses mirror this too. So, if you wanted to express the loss of, say, 20, it will be double 10. That is, minus 13. Remembering 3s and 10s is all that is really necessary to fake it, like a real engineer. Just before we leave the idea of ratio being expressed as a log, let's briefly look at signal strength of power as it To try to appreciate the power levels involved, let's examine some of the familiar values we may already have heard about. We may have used a 3 kilowatt electric fire, that's 3000 watts, or a 1 kilowatt kettle, 1000 watts, a 750 watt microwave oven, or an old 100 watt light bulb that could well now be replaced today with a 5 watt LED lamp. All of these are massive values when we compare them to the power levels used in low power radio. Transmitted power rarely exceeds 0.1 of a watt, and by the time it gets to the receiver kilometres away, that could easily be reduced to 0.000000001 of a watt. All of these zeros just introduce inconvenience and potential errors. So, remember the decibel and tens again. 10 kilowatts, 1 kilowatt, 100 watts, 10 watts. Follow the pattern. We can see here that using the dB reduces the range of tens of thousands to thousands of millionths with all of those zeros to just a range of 40 to minus 40. As watts are too high for radio, we can shift the whole table to express the power in milliwatts, thousands of watts, just like this, and the units change to dBm. It's not intuitive, but the pattern revealed that 0 dBm is 1 milliwatt, with minus 10 dBm being a tenth, and minus 20 dBm being a hundredth, and minus 30 dBm being a thousandth. We can pull the old trick of threes again. Minus 3 dBm is half of 1 milliwatt, 500 microwatts, minus 6 dBm being 250 microwatts, minus 9 dBm being 125 microwatts, and minus 12 dBm being 62.5 microwatts. Oh heck, it may just be as easy to play the full 3-minute video while I go off and make a cup of tea. Flux budget is the nicely antique way of describing any high-tech radio link. Here we can once again gain a feeling of what is happening in our links and describe them graphically. Take this as a simple example. We begin by generating the signal and sending it to an amplifier. This signal then needs to be taken from the output up to the antenna. Here it's liberated into the ether and some is received by a remote antenna down its cable to the receiver for reamplification. At every stage the signal is subject to some gain. Let's draw this in, explaining that the signal can only experience loss in the cable connecting it to the antenna. From the previous section, we know that a well-connected, well-tuned antenna will appear to provide some gain in the link. This is followed by the greatest loss as the signal is transmitted to the receiving antenna. Here, once again, it's subject to gain, to suffer more loss in the feeder before being sent to the receiver. Some say engineering is a black art for geeks, surrounded by secrecy like the magic circle, and cite dB as a totem. In truth, it's a deceit, as it's only used really to make things simple. We could describe the gain or loss at each stage in, say, percentages, like this. As we move through the chain, we would have to multiply each of the values to see the power at each stage. Quite a calculation, and subject to error. Enter the dB, the decibel, deci meaning a tenth, and bell after the American scientist. I know that it's not helpful to say that dB is just a ratio, and I know it's even less useful to say that it's also expressed as a logarithm, but stick with this. Decibels equals 10 log to the base 10 of a ratio. That's the maths, but just remember some magic numbers for everyday use. A gain of 10 is 10. A gain of 100 is 20. A gain of 1,000 is 30, and a gain of 10,000 is 40. You see the pattern? You can keep going. Knowing this, you can see why the gain of 1 is expressed as 0 dB. Don't stop. Go further. Two other useful figures are that a gain of 2 is 3 dB and a gain of 4 is 6 dB. And of course, this is reflected here. So now you know the dB code. That is it. But why? Well, notice how the use of the log has compressed the scale of the numbers from millions to millionth to just plus 60 to minus 60. And the scale is easier to plot. It's a new and more convenient currency, but there's more. Going back to our link, we can convert the losses. With the logs all lined up, that horrid multiplication disappears. All we need to do is to add all of the inline losses and gains. We are in meerkat territory. All we now need to do is to convert the power of 1 milliwatt into dB. We said dB is a ratio, so how can an absolute power level be converted into dB? Well, the measure of power is the watt, so the equation would be dB equals 10 to the log base 10 of 1 milliwatt over a watt. So it follows minus 30 dB when compared to a watt. We can make this a little simpler by comparing the power to something a little more reasonable in RF circuits. Let's take 1 milliwatt as our reference. This gives dB equals 10 to the log base 10, 1 milliwatt over 1 milliwatt. And we end up with 0. And to record this related to a milliwatt, we say dBm. 1 milliwatt is therefore 0 dBm. Doesn't mean there's no signal, it means it's 0 dBm, the ratio. Let's have a quick wave quiz. Question 1. What must all waves do? Answer: move. So this situation in my simplified world cannot happen. These waves have to move. Happy now? So what would happen if we were to drive this wave against a wall with a small hole in it? Forgetting any reflection, the wave would travel through the hole and spread out very slightly. What happens if we narrow the hole? The wave spreads out even more. If you don't believe this, try squinting through a small hole and observe how light waves are magnified. The inverse of the hole in the wall would be a wall in the hole. And if we run the simplified wave model again, we find that the wave wraps around the wall and bends in the same way as passing through the hole. The amount of bend, or diffraction as it's called, is based on the ratio of the size of the hole and of the wavelength of the waves. Question 2 is then, what happens here? This time the wave rushes at 2 holes. Well, running the model up to this point, the actions are exactly the same as a single hole, but running the model further involves the imposition of 2 waves, causing interference. Question 3. How do waves add? Well, here is a special case of 2 waves of the same wavelength happily travelling along together. Their peaks and troughs are together in phase, as we would say, and so the 2 signals add, doubling in size or amplitude. Observe what happens to the amplitude if the phase difference between the 2 is increased. When the phase difference is equal to half a wavelength, the peaks match the troughs and vice versa. They exactly match and cancel one another. This is signal interference and can be constructive or destructive. Keeping increasing the phase, and we cycle through points of constructive and destructive interference. Looking back at the 2-hole model, we see that around the 2 holes are points where the 2 waves are constantly constructive and constantly destructive. The position where the peaks and troughs constantly meet are called antinodes, and the points where there is a constant cancellation are called nodes. Question 4. Have you uncovered the lie told in question 1? Well, not exactly a lie, but let's rerun the initial model with a particular wavelength and run the wave against a plane wall. The wave is reflected. Taking a side-end look at the wave approaching the wall in blue and the reflected wave back in red, we can see where, in this condition, the 2 always constructively interfere, shown in black. If we viewed this from above, our model would appear to have waves that did not move. They would appear to be stationary, a special condition of the incoming and outgoing moving waves. So it wasn't a lie, but a strange thing to observe. 5th and final question, what have I missed? The simplified wave model here could be run in a deep fish tank. All of the waves exist on the surface of the water, not affected by the bottom of the tank. To discover the effects of the bottom, we could slope it up and run a test. After all, something happens at the seaside exactly where the bottom of the sea comes up to meet the surface. Rerunning the model over the shadow end causes the waves to bend. This is called refraction, and we will discover all of these effects now looking at the behaviour of radio waves. A mirage, or even the same effect from a hot road on a summer day, displays how light may be bent in hot air. The mirage is an image carried over the horizon and is due to refraction of light. Radio, like light, also being an electromagnetic wave, suffers the same effect and could extend the range of any signal. It is mentioned here for completeness and unlikely to be important in IoT radio. Another is reflection. As light is reflected by mirrors, so is radio. At night, a reflective ionic layer forms high above the Earth and reflects radio waves back that can be used for very long-distance communications. Some very powerful long waves can be transmitted all around the Earth. Again, this is unlikely to affect LoRa on a global dimension as the power levels are too small, but other reflections could cause signals to bounce from, say, a large metal object, a water tank, a steel frame building, so that it could be received where there is no direct signal. This is an example where the existence of the reflection could be useful, but we will have seen in the Waves quiz that a reflected signal can combine constructively or destructively over an area. If the receiver is at a node, it will receive no signal at all, whereas double the signal could appear at the antinode. This is why some devices have two diversity antennae. They both can't occupy the same node by design. Another reason why signals may not be received is because of diffraction. Diffraction of radio signals could be experienced in a hilly or mountainous area. See here, where low frequency signals will tend to hug the terrain, whereas the higher frequencies will not be received. We can now apply this appreciation of how radio waves behave and get the best from our system, but LoRa and LoRaWAN both have some other built-in benefits, which is why they were designed. The best signal occurs when the endpoint and the gateway are in close proximity, but as we've seen, the attenuation increases as the distance increases. Eventually, the power of the received signal becomes unusable. This could be likened to trying to hold a conversation at a greater and greater distance. Now consider the same situation as a noisy party. The temptation is to raise your voice, but little is achieved if everybody shouts at the party. Or, in radio terms, all this does is drain the battery even more rapidly. An option would be to speak more slowly and clearly. This is what LoRaWAN does, electronically, and it's called the spreading factor. As the distance increases, the signal is sent with the spreading factor stepping from 7 nearby to 12 at a distance. If every communication was just allowed to follow this pattern, the temptation would be for the whole network to slow down. To stop this situation from occurring, there's another rule that limits the total amount of time any transmission can take, and this is quite draconian, just 1% of the allowable time. Short-range communication speaking rapidly can therefore pass more data at the higher rate than the more language can do at distant extremes. This trade-off of distance against power transmitted and quantity of data sent is covered by the heading data rate that ranges from 0 to 6. 0 at the extreme and 6 nearby. Understanding this feature of LoRaWAN is quite sufficient. For completeness, I will overlay this graphic with the details used in the UK and European implementation of LoRaWAN, bitrate, and finally receiver sensitivity. The gateway and each end device may be programmed to negotiate their optimum individual data rate based upon their local settings. This is called ADR, Adaptive Data Rate. Everything is done within the end device to increase battery life and to reduce the power consumption. This even includes turning off the radio receiver and putting any processor into a sleep state. Of course, any detection circuitry or timer has to be able to prompt the device to burst back into life. If the device has anything to say, the LoRaWAN protocol allows the device just to wake up and transmit, without any consideration of any other existing conversation it may interrupt. Once the transmission is completed, the end device listens for a response from the gateway. In fact, there are two very small windows of reception where it's sensitive. Sleep will then follow if nothing's received. The important point here is that the power-saving strategy means that the gateway can only send data to the end device just after that transmission has been sent. No other time. It must await the next end device transmission before anything can pass across the downlink. This style of operation is labelled Class A. We can allow A to stand for all, as every LoRaWAN end device must be able to participate in this manner. Class C devices typically have sufficient power to remain in receive mode constantly. They will begin in Class A but then negotiate promotion to Class C operation. As an aide-memoire, we can let C stand for continuous. They do not fall to sleep and only stop receiving when they are transmitting. So, what about the interim Class B? Name this beacon, as the Class B device listens more attentively than a Class A device, synchronizing its listening with a timed beacon transmitted by the gateway. All of these power types now combine to demonstrate how a gateway can communicate with thousands, possibly tens of thousands of endpoints. A plain radio signal carries no information, apart from the fact that the transmitter's been left on. The signal has to be modified in some way to be used to convey information, and there are a number of ways in which this can be done. Two of the most popular methods are to modify the amplitude and the frequency, and these will be familiar from the fronts of the traditional radio, AM and FM, amplitude and frequency modulation. Listeners to AM radio will be aware that it's more susceptible to interference from natural and man-made sources because it's not as sophisticated as FM, which is clear and resilient, and is a more complex and unnatural waveform. AM and FM will be easily recognised because of their widespread use in broadcasting. Here, we're not concerned with music and speech, but just binary ones and zeros. Digital 1 and 0 signals could be sent using AM by just keying the signal on and off. Crude, but effective. With FM, one frequency could be used to represent a 1 and the second for a 0. This is also a common method and called frequency shift keying, FSK. We can see this signal jumping between its two frequencies here and recorded below in what is called a waterfall display. FSK is important as it's simple to produce and detect and is referred to in LoRa radio transmissions. But LoRa goes further and in doing so becomes more complex and even more resilient to background noise. Rather than just use the two frequencies of FSK, it sweeps between the two like this, up and down. Now, there are two parameters that may be changed on both the rising and falling signals. These are the rate at which the sweep changes, call this the sweep rate, and the range over which the sweep could change, call this the bandwidth. There are always compromises in communications, and here there are compromises in both sweep rate and bandwidth. Increasing the bandwidth provides a better quality signal, but bandwidth is at a premium. Everybody is vying for space, and bandwidth is valued and restricted. Engineering involves maximising performance using minimal resources. Bandwidths specified for LoRa are therefore restricted under international agreement to 500 kHz, 250 kHz and 125 kHz, and in Europe further restricted to just 250 kHz and 125 kHz. A slow sweep rate is easy to decode and becomes progressively more difficult the faster the change. Here's another potential trade-off. The faster the sweep rate, the more information can be passed, but the more difficult it is to accurately resolve the signal. The European system uses 6 different sweep rates, or spreading factors as they're referred to. These are referenced by numbers 7 to 12. We've already seen that LoRa devices use a LoRa, which is a protocol where any device can just wake up and transmit, regardless of any other existing conversations. As an alert, a device will start by sending this unique training cycle of 8 up sweeps followed by 2 down sweeps. We can break these sweeps into symbols of equal period. The block of 8 is called the preamble and followed by 2 symbols used for timing, called the synchronizing symbols. Any listening device can clearly recognize this preamble as the beginning of a packet, which alerts its attention. The transmitting device is then time limited by which it must complete the rest of its transmission. All of the data content of the packet is contained in the following symbols. Each symbol contains a discrete frequency step representing 8 bits. The data contained in each sweep is probably best shown using these examples. The details, like all good comedy, is in the timing. The metadata now received with the data can be assessed. Channel 1 is the radio channel used to communicate. Date R is the communication spreading factor with the bandwidth of 125 kHz. Freq duplicates but confirms the frequency channel of 1 as 868.3 MHz, and LoRa is the modulation scheme employed. This leaves the 2 readings of LSNR, the signal-to-noise ratio, and the RSSI, the received signal strength indication. These values can be seen in this display, where all of the signals can be seen as being quite vague, as they are so small. The RSSI is the measure of signal strength, measured in dBm. It's an absolute power level, and the signal-to-noise ratio is just that, a plain ratio of the 2 power levels, signal and noise. Noise, or the power of the noise floor, may be seen here in blue. Noise is random, and by its nature therefore difficult to characterise. Add this to the fact that we now know our spread spectrum signal can operate below the noise floor, and we end up with some real challenges in trying to obtain some meaningful figures for our test equipment. The idea of the survey is to become acquainted with the box and the conduit, and therefore the potential performance of any final system. it's necessary to emulate the conditions of the final layout as closely as possible. Full sweep tests all of these options. Position the conduit as close to its final location as high as possible. Orientate the LoRa WAN antenna vertically. Try to keep it away from any obstacles that cause attenuation. Metal water tanks in lofts are a typical obstacle. Keep it away from other sources of electrical noise. On top of roofs, these could be lift motors, other transmitters and air conditioning units. Turning to the box, scroll down to the Sweep Survey option and select. On a pristine unit, you will jump straight to the survey screen, but otherwise you will be presented with the Erase or Append to existing survey data file. With these options, SW2 Erase and SW1 Append. The box has a small memory in which it stores data. We will be looking at that shortly. So, for the moment, erase, if you wish, which, in the good practice we have come to expect from Multitech, you are asked to confirm. The plain Sweep Survey screen is displayed with the SW2 Sweep option presented. Be prepared, as the sweep begins immediately when pressed. It may be pedantic, but secure the box with its antenna vertical and in position before starting the sweep. Then retire, as your body can influence the radio signal. The screen cycles through 28 testing options which are presented as they are completed. The box steps through increasing power levels from 2 dBm, 8 dBm, 14 dBm and 20 dBm, and decreasing data rates starting at 6 and reducing to 0. This displays the results in real time. The idea of the sweep is to test the performance of the link with varying power levels and spreading options. Remember, the aim of any final system is to accommodate as many nodes with the clearest signal. A low power P equals 2 short spreading factor, S equals 7, data rate 6, node nearby, can send a lot more data and burden the network far less than a remote node on full power, on a spreading factor of 12, data rate 0, draining its battery, limited to sending only 50 bytes at a time. Each sequence of a sweep is given a unique number, here ID 1. DR is the data rate, and P the power level. Each full sweep takes 2.5 long minutes to complete, but it's not unusual to see a few failures, but once finished, these can be viewed on the display. To see the results, press SW1 to return to the main scrolling window. Scroll through to select View Data and select to see the results that may be cycled through using this next option. This is a sweep record identifier, the data rate and the power level. Below is the up margin in dB and the number of gateways seen. The dialing figures are recorded, and here is where pressing Next and Back button take you through the recorded data in the form I call immediate mode. What I would like to see is this sort of presentation, or data extracted into Node-RED at least. This is all covered in the following videos, but in this final section we will use the M.dot to recover data. We will go through the process of recovering sweep data from the box, not because it's the most convenient method, but because it includes the process of connecting another important component contained in the startup kit, and, to be honest, also has a few gotcha traps for the unwary. This is the M.dot Micro Development Kit. It has a slot for an M.dot and a USB plug. Here it needs what I must, to be consistent with M.dot's naming convention, call, to avoid any possible confusion, an 8-position flat programming cable. This is supplied in the kit. Before it's used with the M-Box, it's best to install any available drivers and software and prove the link to the M.dot Micro Development Kit before proceeding further. All of the communication with the M.dot Micro Development Kit is carried out via the M.dot Micro Development Kit's USB port, and this may require the installation of some additional drivers and software. Communications with the M.dot Micro Development Kit happens in two ways. The first provides a terminal connection, and the second provides access to ARM's Mbed development platform. A good terminal emulator program is required to form the connection with the terminal interface on the M.dot Micro Development Kit. On a Windows machine, a popular choice is TerraTerm, the old faithful emulator that's been around for almost 2 decades now. It's free and open source. Pop over to osdn.net. Once installed, insert your M.dot Micro Development Kit into any USB port, and the familiar chimes should ring out success. The new File Explorer window will open as part of the ARM Mbed development environment. It can be identified as typically it contains 3 files: details.txt, file.txt, and mbed.htm. It's good to receive this confirmation that the system is properly working, but we do not need this screen. The use of the embed is covered in the following videos, so close this window for the moment. Open TerraTerm and navigate to Setup Serial Port. There should be at least two options shown in this port pull-down that will vary depending upon the individual settings on your machine. It's not possible to define a guaranteed walkthrough for this section, as the correct comms port has to be identified. If the list is too long, an option that will help with the COM port identification is to see which option disappears when you disconnect the M.Dot Micro Development Kit and restart TerraTerm. Otherwise, work through the available ports one at a time and change the baud rate to 115,200. Leave the other options as data 8-bit, parity none, stop 1 and flow control none. Click OK. Insert the 8-position flat programming cable, making sure to observe the polarity defined by the red wire. Turn on the box. If nothing happens, disconnect and reconnect the M.Dot Micro Development Kit USB connection. The box should restart and the TerraTerm window display some trace information. Now select Configuration from the box menu. If this does not appear in the TerraTerm window, mouse click into the window so that the cursor starts to flash and enter until the OK response is seen. What you have here is terminal control of the end device in the box using AT commands. This is a style of command that harps back to the old Hayes-compatible modems of the 60s. Try entering AT&V to see details of the device, or just enter a question mark to see a list of commands. And enter the special command for the box AT plus GSDF, standing for Get Survey Data File. All of the data stored on the box should be revealed. The first line displays the meaning of each column, and this is what we're going to work with here. ID is a simple sweep identifier. Status is S for success and F for fail. Lock provides confirmation of the GPS locking to satellites, followed by latitude, longitude, altitude, and time of the recording. Gateways is the number of gateways seen. And then the important values: margin, RSSI down, SNR down, data rate, and power. How accurate is the box in recording data? Is the information repeatable? For these tests, we need to nail down as many variables as possible. The conduit and the box are securely located in clean, dry, wind-free locations with both units placed on earth metal plates, 5 lambda high and 10 lambda apart, sequentially during daylight, avoiding any variations other than the human pressing the sweep button and retiring. 8 identical sweeps were taken, shown here as S1 through to S8. The only difference being that the 2 final sets of readings were taken with the box horizontal. The headings are M for margin, R for RSSI, S for signal SNR, D for data rate, and P for power. Are the readings repeatable and consistent? Let's first consider RSSI, the receive strength signal indicator. This is a power level and measured in dBm. What may not be clear here is that these numbers are all negative. The stronger signals are less negative. The strongest signals are highlit in yellow. The range of the mean of RSSI is just minus 81 dBm, strongest minus 88 dBm minimum. Note how close all of the signal to noise ratios are. These are positive and all consistent and strong. The final figure is M, margin. Now margin needs some explanation. Margin is the difference between the received signal strength and the noise floor, and here we really see the power of LoRa modulation. It was mentioned before that conventional radio signals become unusable as their signal-to-noise ratio drops towards the noise. LoRa works below the noise, and the greater the spreading factor, the deeper into the noise it can operate. Margin is the difference between RSSI and this floor. The additional margin is due to what is known as processing gain provided by the spreading factor. If the margin falls to 0, the signal becomes unusable. Margin is the most important figure. Consider these 2 readings taken with the antenna horizontal. The RSSI signal is on average between 8 dBm and 14 dBm down, and the margin 6 dB down. These figures show that the general signal level is low, but very high for a LoRa system. They need to be repeated at a far larger distance. We've covered a good deal of ground in this first video, where I hope you've gained some feel for the way in which radio waves behave, and how this impacts on testing and implementing things. Whilst it's good to have a nicely mounted, correctly polarised signal, cost and convenience tends to reduce real things to using small wires, little coils, ceramic or PCB printed antenna. Obviously, these constraints restrain the performance of the radio system, but the tests carried out here proved the innate performance of LoRa radio design by producing some impressive results. In the next video, we program the development board to design practical things, dive deeper into security, and investigate how things join a network. We will also show how practical field strength measurements can be directly plotted onto web-based maps.